Okay. Yeah. So today we're talking about side channel analysis. So as we know, cryptographic implementations are broadly pretty secure, but when they're in the physical world and they can get in the hands of attackers, then we have to account for physical leakage, which can leak information about internal values and which we can use to derive the secret key. So examples here are power, electromagnetic emanation, timing, and others. So differential power attacks are attacks that leak, based on the power usage, leak some internal value. So generally, we assume some leakage model, for example, the Hamming weight, and then we can take a bunch of measurements from a device that we're attacking. And when it's running cryptographic implementations, then we model the leakage. Generally, we assume we have a known input and an unknown key. Then for this leakage model, we can generate hypotheses for the measurements for all possible key values. So generally, we're attacking a byte, so it's 256 possible keys, and we just measure the correlation or or we match these labels for each possible key candidate to the traces, and the key that best explains the traces will hopefully be the key that is actually used. And using this, we can exploit the leakage and extract the secret key. So in profiled settings, we're also assuming we have another device. So a profiling device where we know the key. This allows us to perform worst case evaluations where the attacker has much more capabilities. So this profiling device is generally a programmable device. Here we have the attacker knows the key, and they can arbitrarily program the device and take a bunch of measurements with known labels, so the known Hamming weights of first round output or something. Then we can create, for using all these labeled measurements, we can create a model or template. And this is essentially the same as a classification task in machine learning. And then using this model or template, we can take measurements from the attacking device and guess the labels using this template. Then using the accumulated predictions for these attack traces, we can perform much more effective attacks than in non-profiled settings. So how do you protect? Masking is a way to split the computation into several secret shares. So as opposed to performing the operation once, we perform the operation in two separate shares and then recombine at the end. You do this by taking some randomness at the initial part of the algorithm and then removing this at the end. So as we can see, this unprotected leakage here, this is the y-axis is signal to noise ratio. The x-axis is the time samples for the measurement. And we see that there are, for the S-box output unprotected, we can see that there are several very large spikes indicating leakage in these points in the trace. When we protect using masking, we see that all of this leakage nicely disappears, which is very helpful. However, the computation still leaks, just not directly. If we know the randomness used in the masking scheme, we can still find what the leakage is. So see here, there's no first sort leakage, so without the mask, we cannot do these attacks. But in the second point, we assume we know the mask, and then we can compute the SNR for the mask in orange and the masked S-box output in green. And we can see that the leakage is still clearly there, but it's not as easy to find directly. An exploitation of these devices now requires finding the leakage for these shares and recombining values somehow, and doing this efficiently. Profiled side channel attacks, the model creation is classification. So because we have a bunch of labeled traces, and deep learning neural networks are also doing classification. So why not use neural nets? We can automatically, using neural nets, we can take full-length traces. We don't have to do a bunch of the feature engineering that is generally required for normal profile attacks, and we can automatically defeat masking countermeasures, misalignment. We can deal with very, very long traces and combinations of these. However, dealing with, if we know the masking randomness, attacks are relatively easy because we can select only the subset of samples that actually leak. So if you recall the previous 2 slides ago, you just select the high SNR peaks and profile on that subset of input points. This is fairly straightforward to do. Neural networks work really well here, or you can even create templates for the individual shares, predict those from the trace, and use attacks like Saska and post-processing mechanisms to exploit the key more efficiently. However, attacking the raw traces using deep learning is still possible but difficult because you have the maximum accuracy is low. If you have leakage for 2 shares and it's it's noisy and you can't perfectly derive each of these shares from the trace, then you cannot perfectly predict, and your accuracies are generally about 1%, if not lower. Or 1% would be really good. Furthermore, the traces are mostly noise. So we have a whole bunch of points that are only noise and not relevant to our task at all. So the models tend to want to maximize their accuracy, and they can memorize all of the rest of the points to increase their accuracy, and this makes optimization very, very difficult. Furthermore, if we don't have the masks, we can't do feature selection, so we have to deal with this problem somehow. So the key question for this project was, can we do this feature selection without masks? So our threat model, very briefly, so we're assuming a scheme-aware threat model where we have a profiling model, a profiling device with a known implementation, but we don't have access to masking randomness. In evaluations, this can happen, or because the masks are stored in protected registers. This is a fairly common threat model. So what we then introduce is a reference implementation on a similar device with a similar masking scheme. And here similar is very vague, and I apologize for that. On the reference device, because we really fully control this device, we use the known masks to do feature selection, and then we attempt to emulate the feature selection that we do on the reference device on the target device. So very briefly, we use conditional GANs in this work. What they are is essentially 2 networks that we train adversarially. So in image generation, we have X-real is a real image, X-fake is and fake images generated by the generator from noise. The discriminator tries to distinguish between real and fake traces, and the generator tries to fool the discriminator, and you train these adversarially. This becomes a min-max game. And the conditional GANs are similar, but you just add a class label. So for example, you say, oh, this is an image of a dog, and then you can control what type of image the generator generates by also including the label there. So our framework is then in the scheme-aware threat model. We include the reference device with no masks, and we train the CGAN to take profiling traces, to input profiling traces as opposed to noise, and we imitate the feature selection from the reference device on the target. So more concretely, we have in the top we do reference. We have the reference device with no mask. We do white box feature selection in some way. We then take the profiling traces and use the generator and discriminator to train a feature extractor for the target device, which we can then use to, in the bottom, just do a conventional profiling attack on the extracted features using the generator. So we have several targets here. I won't go through them too cleanly, but we essentially have 3 8-bit devices with EM power measurements, which implement either Boolean masking or OSM masking, and then we have 2 32-bit devices, which implement Boolean masking. So our results. Firstly, we see that on the left we have the reference leakage pattern that we include. So in these images we just make the patterns arbitrary to see if our generator can extract the leakage, and it matches this pattern very nicely. And as we can see, it matches quite closely. And so our attacking results. So we compare to white box attacks where we use the masks, and as we can see and black box attacks. So the black box attacks are just attacks on the raw traces, where we don't do anything outside of conventional deep learning based attacks, and we can see that our attacks are pretty far away from the black box because we're in blue, and we're generally in between or still slightly worse than white box depending on the target, but much better than the black box attacks. So the similarity. The necessary similarity is quite vague still. So the masking schemes, we kind of assume the masking schemes are broadly similar. So essentially, if one target is implementing Boolean masking, then we want our reference device to also implement some kind of Boolean masking scheme. Although the DPA scheme is fairly different from the ASCII scheme, and it still works quite well. For the device similarity, the closer the device, the better. So when we have two 8-bit devices and the leakage is very strong in both devices, we see that the attacks become much, much better, and we really approach a white box setting. However, when we use more, when the leakage varies more from the reference device to the target device, we know that, we see that attacks still improve over black box attacks, but we don't tend to approach the optimal attacks that we know can happen. So overall, the idea is that we want devices that are as similar as possible. So you would want, if you're doing this practically, in an ideal setting, you take an open source implementation of the same masking scheme, you adapt it to be able to extract the masks, you take a device model that is as similar as possible, preferably identical, and you essentially do the same thing. This is in our ASCII versus ASCII scenario. These are two slightly different measurement setups on the same device model with the same implementation, and then our attacks are essentially the same as white box attacks. In ideal settings, but differing implementations can still allow for improvements. And yeah, using two different models or two different devices is bad. So also, if these devices also these implementations are all byte-based. If we have bit-sliced implementations, this is probably too different. So then presumably you can't use a bit-sliced implementation as a reference and then a byte-based implementation as a target. Similarly, you wouldn't want to use a hardware implementation as a reference or target when you're using a software implementation or a byte-based implementation as a reference. But here, the similarity is, again, still horribly vague, and this is a great target for future work. So to conclude, we can use reference devices to improve attacks. Given the right training setups, neural networks can exploit extra information from these reference devices, and this really helps a lot to improve the difficulty of finding profiling models. And in future work, we've already done some work that waives the scheme awareness, so we can do the reference device without knowing what scheme is happening there, and we just use unprotected leakage, and we can kind of distill, we can still use the leakage information that is happening on the reference device, we can still emulate the leakage that's happening on the reference device without knowing precisely what is happening on the target device in terms of countermeasures. And we plan to explore more options in generative training structures that can help. So I have some time left over, so I will quickly maybe go over some extra results. So yeah, some more detailed attacking results. So in this table, which hopefully you can read a little bit, we have different reference. So in this case, it's the ASCII versus ASCII cases. We see that our attacks all exploit can all work in one trace. With slightly different implementations, it takes slightly more traces, but we're still within 10 traces generally. Then for the DPA target, with again, we quite significantly improve over black box attacks. So the red axis are where attacks don't work, and we see that we need between 300 and 140 traces and 1,500 traces to break 3 key bytes, and then to only break 3 key bytes. And then when we use our setup or white box setups, we can break it within 10 traces across the board, which is a nice improvement. For the chess CTF target, which is the 32-bit target, we still use 8-bit reference devices. We see that we quite drastically improve over black box attacks. In this case, we can't do white box attacks because we don't have the masks. And then yeah, for eShard, it's similar to chess CTF. Although here we also see that for some reference we don't improve at all. In fact, using DPA as a reference, we see that we kind of regress from black box attacks, where we can still break most of the targets. But using a more appropriate reference, we're still pretty similar to black box attacks. Especially using the top row, we improve a bit over black box, but here it's very. It doesn't help too much in this case. So yeah, the reference, how close the reference is still quite relevant. Yeah, I think this is about it. So then I can take any questions.
Questions?
So what type of random data you are using? You have mentioned that DPA and ASCII. So actually at the core, what type of random data is being used for masking?
I know these implementations use Boolean masking. I'm not sure what.
So whether that is a pseudo random data or something else, it is having some known, I can say, partiality or biasness. So that becomes important. What type of masking you are using? So if you can.
So yeah, I can go back a bit. So the Asiacrypt implementations, they use some Boolean masking scheme, and DPA is fairly different. So in DPA, we know that the masks can only take 16 values, and we just have 16 different S boxes. But the Boolean masking schemes on all of the other ones are similar, although their specific implementations differ to some extent. But yeah.
Thank you for your talk. Did you try to train on a different masking order than you have then on your target device? So, I don't know, have the profiling on the first order design and then our target the second order design is?
So that way around, I don't think that would work, but in the work that we do have some work that does so in the 10, the LDPA work that we're doing, we do the reference is first order, and we do first order leakage, and then the target is second order leakage, and this works reasonably well with some other optimizations to further improve the training structure. The other way around, I think if you're using higher order reference than target, I doubt this helps at all, because then the leakage would have to be split into two shares, or the generator would have to split the leakage somehow into two shares that match target. I don't think this makes too much sense. But the other way around, I think it can work.
Okay, thank you.
Okay. So we started a bit late, so in the spirit of trying to make up for some time, let's thank the speaker again. So I'll introduce the talk while the speaker gets ready. So the next talk is ZK fault attack analysis on zero knowledge based post-quantum digital signature schemes, and the talk will be given by Pooja.
So, hello everyone, thanks for joining today. I am excited to present our work titled ZK fault attack analysis on zero knowledge based post-quantum schemes. Cross and lace. So let's start. So as we know that NIST have selected 3 signatures as post-quantum standards, and among them 2 signatures are based on the Latin problem. So NIST organize another additional signature standardization process to diversify the post-quantum options. So in this direction, 40 schemes has been selected in the first round, and 14th scheme has been entered in the second round, and our attack is work on these 2 schemes, cross and lay, and both of these scheme uses a common zero knowledge based framework. So here prover has the information of public key, public information and the secret information, and prover wants to prove it to the verifier. So prover first generates a commitment and send it to the verifier. Then the verifier samples a random challenge and sends it back to the prover. After that, prover generates a response with help of all of this information and sends it to the verifier. Then the verifier verifies whether all of this information are valid or not. If all of this information are valid, then the verifier will accept it, otherwise it will reject. Now the Fear-Summit transformation is used to make a signature scheme from the previous interactive zero knowledge based framework. So here the signer play the roles of the prover. So the signer generates all the commitment, and it also generates the challenge by itself by using this commitment. And then the signer generates the response and then send it to the verifier, and the verifier verifies whether all of this information are valid or not. Now I will explain the layer signature scheme and the attack methodology on this scheme. So here first signer generates a as many monomial matrices, secret monomial matrices and one public key G0, and then all the other public keys G1 to Gs are generated by using the secret key and the corresponding public key G0. So here this secret key Q1 to Qs are used multiple times to generate the different signatures. So our target is to recover this secret key by our fault attack. So for each signature, the signer generates T many ephemeral key Q1 dash to Qt dash, and then by using this ephemeral key, the signer generates the corresponding GI dash, and then signer generates a commitment, and after using this commitment, it generates the challenge, where each value of this challenge is realized in between 0 to S, and depending on this challenge, the signer computes the responses and then send it to the verifier, and then the verifier will verify it whether all of this information are valid or not. So here observe that if the challenge value is 0, then the signer stores the corresponding ephemeral key as a response. Otherwise, the signer will store the secret related information as a response. So we cannot get both the information at a time. But if we can get both the information for a fixed challenge value, then we can easily compute the corresponding secret matrix. So in our fault attack, our target is to find a pair, the ephemeral key and the secret related information for a fixed challenge value. Sorry. So so in this work, we assume our fault assumption is we can change the value of our targeted location from 1 to 0. So this fault can be achieved by any one of this fault model. I mean, bit fault, the stuck at 0 fault, and the instruction skip fault. So as a result, we can recover the full secret of lace and cross with just one fault from one faulted signature. Whereas there is only one parameter set, lace 1s, for which we require approximately 2 faulted signatures to recover the full secret. So now I will explain the overview of lace so that I can explain the fault methodology. So here each of these ephemeral key is generated from a random seed, and the challenge value is a fixed weight W. So there will be T minus W many zeros inside this challenge seed. So the response must contain the information of T minus W many seeds information of the ephemeral key QI dash. So it takes a huge size of signature. So it's around 75 kilobytes for less 5K. So in this reason, LESS uses the GGMT construction to reduce the signature size. So after using this GMT construction, it compresses the signature size as much as 57%. So here first signer generates the ephemeral key by using the GGMT construction, and we call this GGMT as a seed tree. And then using the challenge value, the signer first generates a reference tree, which is a binary tree, and this is generated based on the challenge. And third step is, depending on this reference tree, the signer decide which nodes of the seed tree will be published and which node of the seed tree will be hidden. And our fault location is on the reference tree. So I will explain each step very briefly. So first reference tree. So here first signer samples a random seed and store it as a root of the seed tree, and then each node generates its two child node, and child node by using some PRF function, and in this way all the leaf nodes is generated, and from this leaf seed the ephemeral key are generated. So now I will explain the compression technique with some small example. So suppose our challenge value is this one. So then we have to publish the seed of the corresponding nodes, red nodes, and we have to hide the gray node, corresponding gray node for non-zero values. So we want to, because we want to publish this corresponding this ephemeral key, and we want to hide the ephemeral key corresponding to this gray node. And instead of publishing the ephemeral key, we will publish the secret related information corresponding to this gray node. So now we will generate the reference tree with by initializing the initialize first the leaf node. First we will initialize the leaf node. So now we will update all other nodes of this reference tree by using maintaining this statement. I mean, if both of the children are red, then its parents will be red. So in this way, we will generate the reference tree. Then using this reference tree, we will decide which node has to be published and which node of the seed tree has to be hidden. So we will check that for each node we will check that whether this node is red or is parent and its parent is grey or not. If this happens, so then we will publish the corresponding seed. For example, for X1 and X12 and X13, it will satisfy this condition. So we will publish this corresponding seed. So here we can observe that if we have the information of the intermediate node seed 1, then we can generate all of the leaf nodes by corresponding leaf nodes, seed 7 to seed 10. So we can get the corresponding value of these ephemeral matrices. and then by comparing, by checking the challenge value, we can compute the value of the corresponding grey node. The secret related information of the corresponding grey node. So now observe that if we change the value of a grey node to a red node, then the things may change. If we target the value of the grey node X5, then by fault attack, then it will publish this corresponding seed, seed 5, because the value of the seed 5 is red and its parent is grey. So from this information of seed 5, we can generate the information of seed 11, the leaf node information. And this information, from this information we can generate the corresponding ephemeral key Q-5. And also note that we are changing the value of X5. So the value of the challenge value, corresponding challenge value is still now unchanged. So from there we can generate also generate these two secret related values. So for the challenge value, fifth challenge value, we can generate the ephemeral key, and also we can generate the secret related information. So from these two information we can get our secret. So it leaks the secret information. However, X5 is is not the special node. If we target any of these grey nodes, then we can get the secret information. However, if we select the nodes with higher height, it would give more information about the secret. Suppose if we select the node X2, then it will provide us the information of Q1 and Q2 corresponding to the leaf node X4. And for our result, we have targeted the location either X1 or X2. So after fault injection, we need to answer these two questions. Is the fault injected exactly at the ith location, or is the fault injection is successful or not? If these both, if we answer both of these questions, then we can find our secret correctly. So in our work, we provide a fault detection method that answer both of these questions. So now the question is how to prevent the fault attack. So here we can observe that after the challenge generation, first the challenge is used to generate the reference tree and tree X, and depending on this reference tree, the response is generated. And in the second step, it will check the challenge value, check the challenge value and then store the secret related information. So if we target this, in the first step, the value of, if we change the value of X by injecting fault attack, then it will, it will not hamper the second part. So we can get the corresponding secret related information easily from the second part. So for this reason, our attack will be successfully done. So we can merge these two parts, these two steps, such that if we merge these two steps, then we can avoid our fault window. So our first countermeasure is we ignore the reference tree generation part, and we will compute the response by checking the direct challenge, the challenge part, each of these challenge. So in this way we can you can prevent our fault attack. But this method takes the huge size. If we use this method, then the signature size will be increased, because we are not using the compression technique we are ignoring the reference tree. And the second countermeasure is we can ignore the second part, and we generates the secret related information by using the reference tree. And by using this method, we can keep the signature size same. So in conclusion, we show a fault attack on cross and lace, and our proposed fault detection method prevent erroneous secret recovery. Also, it can be realized by many fault model such as bit flip fault, stacker 0 fault or 1, and instruction skip fault. And this fault can be applied to any other scheme those uses the same similar GK structure with compression technique, for example mate. And we have proposed 2 countermeasures to prevent the.
Thank you. Questions?
Thanks for your interesting talk. I had a question. You, in one of the slides, you thought you will always target X1 or X2. Why would you not target X0?
Okay. Yes, because there is a condition. Publishing the seed. The condition is the node should be of red color and its parent should be of gray color. So for X0 node, it is gray already, and if we inject the fault, then it will be red and its parent will be red. So we cannot get the seed value, corresponding seed value from this node.
Okay, thanks.
We have time maybe for one more question. Okay, so I have a question. So when you say that you target the GGM tree computation, right? So do you need a single fault injection during a particular signature generation, or do you need multiple fault injections? Okay, and you basically just have, so you do not need the scheme to, let's say, generate multiple signatures on the same message for these 2 ones. So you are able to, like, if it only generates, let's say, a signature per message, you are still able to recover the secret key, or do you need the protocol to repeat for the same message multiple times?
Actually, as you can see that our result, we can get the full recovery, full secret. So we can get the full key, but just for just one fault signature. So we need only one signature as a signature to recover the key.
Okay, okay, thank you. Okay, okay, so let's thank the speaker again. Okay, so that brings us to the last talk for this session. This talk is on formal definition and verification for combined random fault and random probing security, and Jacob will give the talk.
Thank you for the introduction. Yeah, so this is a joint work with people from crypto experts and who visited Bochum. So usually if we analyze cryptographic algorithms, then we assume a black box model where, for example, if we look at encryption, we could have the following game where we have an adversary who selects 2 arbitrary plaintext from the plaintext space, sends it to our algorithm game, which will choose one of those plaintexts randomly and sends the encrypted value back. And then we say that the algorithm, the encryption, is secure if the adversary cannot determine which of those 2 plaintexts was chosen by the algorithm. And this is a black box model because we really assume that the adversary only gets or the only knowledge that the adversary gets is the encrypted part of the encryption of the plaintext. However, in the last two talks, we have seen that this is not always the case if we look at real implementation of cryptographic algorithms. So in particular, if we have an adversary who has close proximity to the implementation of the algorithm, we can, the adversary can observe the physical execution environment to perform some side channel analysis, which will leak additional information about the internal value of the encryption. In addition, we have seen in the second talk that you can also perform some fault injection, so manipulate the physical execution environment to provoke faulty output, which might also leak some information about the secret. And in this talk, I want to look at an adversary who is able to do both, so can inject faults and perform side channel analysis and do both at the same time. But I want to abstract away from specific attacks, but talk about general models, how to argue about security or insecurity in those settings. So let's focus first on the side channel part of this. And one classical method of analysis, or a usual model for analysis, is the so-called threshold probing model. So here we assume an adversary who has access to the structure of the circuit, so knows the gates and the wiring, and then is able to select a certain subset of wires, so in this case D of those wires, of which then the carried values will be given to the adversary. And then we say that a circuit is D-probing secure if the adversary view of, can be simulated without access to any secret. So this means then that it is statistically independent of the secret, the observation. This is a nice model that allows a lot of analysis, however, has the problem that if you have side channel leakage, you don't get specific values, but instead you get all of the values, but in a noisy case, in a noisy way. So what the literature did afterwards, or basically at the same time, is introducing the random probing model. And this is basically similar to the threshold probing model, but instead of letting the adversary choose specific wires, we now have a distribution which says that each of the wires will leak its value with a probability p, and then we sample one of the wires combinations, of which we give the adversary all the values that are carried by the corresponding wires. And then we say that a circuit is epsilon random probing secure if the adversary view can be simulated without access to any secret with a probability 1 minus epsilon. So epsilon is the probability that the adversary will gain some probe combination that leaks the secret. This is much more general, of course, this model, however, has the assumption that all the values have independent and identical noise in the background. And this is not really realistic, especially not for hardware security, where you have a lot of parallel computations. So some first thing that we propose in our paper is to generalize this model, so to have not a probability distribution where each wire leaks with probability p, but have an arbitrary distribution where the probabilities can be dependent on each other and different. But otherwise it's the same, right? We still sample something from this probability distribution and then say the circuit is epsilon random probing secure if the adversary view can be simulated without access to any secrets with probability 1 minus epsilon. So this is it for, the advantage here is that we can now simulate or model things where we have different and dependent noises. We can model things where we have gates that have different driver ranks and physical defaults such as glitches and transitions and so on. So that's for the side channel part. I want to now talk about the fault part. And here in the literature there is a quite similar model to the threshold probing model, which is called the threshold fault model. And basically, again, the adversary has access to the structure of the circuit, so knows the wiring and the gates. And now the adversary is able to select a certain subset of gates and change the function that is underneath this gate. And the adversary can select up to k of those gates, and then we say that the circuit is k fault secure if the output can always be detected, or so the faulty output can always be detected or corrected then. So this is again a nice and simple model, however suffers from the problem that this assumes an adversary who has really precise control over the faults, right? But if you inject a fault, for example, via Glock glitching, there is no way that you will only target one gate, right? There is a high probability that you will target a lot of gates, and this is not necessarily bounded by k. So what we propose is something similar to the random probing model. So we assume a general distribution over all the faults, of which we will then sample one random combination, and then say that the circuit is mu random fault secure if the faulty behavior at the output can be detected or corrected with probability 1 minus mu. So mu here is the probability that the adversary will inject some fault that is meaningful for the adversary. Yes, so this is the fault model, and now I want to talk about the main part of our paper, which is the combined adversary model, where we have an adversary who can first inject some fault and then have some side channel analysis to exploit more information. And basically this is the same model as the previous two, but the combination of those. So we assume an adversary who has access to the structure of the circuit, right, and then we have an arbitrary fault distribution of which we will sample one fault combination, and afterwards we have one probe distribution of which we will sample one wire combination of which we will give the values in the faulty circuit to the adversary. And then we say that a circuit is gamma random combined secure if the faulty behavior of the output can be detected or corrected, and the adversary view can be simulated without access to any secret with probability 1 minus gamma. However, this already gives us the first interesting point of this definition, because how do we determine this gamma, right? So ideally the gamma should be the probability that there is some meaningful leakage to the adversary. And this is the intersection of the events that there is fault leakage and that there is side channel leakage in the faulty circuit, right? However, those are not independent, which makes it quite messy to work with them. So we define the epsilon slightly different. We take away the cases where we have additional fault leakage, right? So we say this is only the side channel leakage when there is no fault leakage. So when the output can be corrected or detected, any fault at the output can be detected. And this means that now these two events are independent of each other, which means that we can compute the gamma just as mu plus 1 minus mu times epsilon. Another interesting part for this model is the knowledge that the adversary has about the fault that he injects. And so if we assume this small circuit here, so an XOR chain, where we inject a fault into the first XOR such that we have a bit flip at the output with probability 1/2. If we assume an adversary who knows which fault is injected, so what happens in the internal, in the circuit, then there are two cases, right? The first case is no fault is happening. Then basically the adversary who has a probe on this output wire here will observe a value that is statistically dependent on all of those inputs, so the adversary will learn all those inputs. The other case is, right, that we have that the fault is happening. So we have a bit flip, which makes the first gate to an XNOR gate, but again, the output is statistically dependent, and so the adversary learns all of those values. Sorry. Now, if the adversary does not know which fault is what kind of fault is happening or not happening, then we basically turn this first XOR gate into a random gate that generates some random output because we either flip or not flip with probability 1/2. And basically this makes also the second gate, the output of the second gate random because we basically have a one-time pad. And so in this case, the adversary learns nothing about the inputs, which means that indeed the knowledge about the fault has some meaning and we have to differentiate here. So this is why we introduced two different definitions for random combined security. One with unknown fault, which is a more realistic case, because if you have a real device and you inject a fault, then you don't know exactly what's happening there. And the other one is with known faults, which is not that realistic, but much easier to analyze because we know exactly what is happening. Oh, sorry. sorry. All right, I don't want to go into too much detail of those definitions, but highlight a few things. So first, in both of them, we require that the circuit is mu random fault secure. Then we have a difference. So in the unknown fault case, we require a simulator that can simulate the values of the probes by just having the distribution of all the faults. And in the known fault case, we first sample a faulty circuit and then require simulators that can simulate the values of the probes within this faulty circuit. And then, as discussed, we compute the gamma in both cases as mu plus 1 minus mu times epsilon. Okay, and now, of course, it is interesting how those two definitions relate to each other, and luckily we can have a theorem about that, right? So we can say that if a circuit is, known fault secure, then it will always be secure in the unknown fault case with a gamma that is smaller or equal to the gamma in the known fault case. And for the details of the proofs, I refer you to the paper. However, the intuition is that we can construct a simulator for the unknown fault case by first sampling some faulty circuit out of the distribution of the faults, and then use the simulator for the known fault case. Okay, and now what we did is we implemented some two different tools to analyze the security of circuits, and then used these tools to analyze, first I want to talk about composition. So if you have two gates, and I hope you can see it slightly, it's not that good. If you have two circuits that are random combined secure, then the combination will not be random combined secure with the same parameters, so we have some compositional notion. And here we restrict ourselves to the combination of masking, so this is what we heard in the first talk, right? You split the computation into different independent parts and recombine afterwards. And replication, where we compute the value multiple times to then have a majority vote for correction. And basically for composition, we require the same random combined security, however, with additional fault in the inputs. And here we allow that each input share, so a certain subset of the input shares, of the replications of the input shares can be faulted. And that a certain subset of the shares of the output can be probed, however, there we get all the replications. And now to what I was already referring to, so we implemented some tools and analyzed 5 different gadgets that are already known in the literature for our composability notion. And the first one is DOMREP, which is a simple masked multiplication that is replicated in, to have fault security as well. And as we can see, this is not that secure in the combined case, in the composition case, so we have a leakage of almost 1, so the probability of leakage of almost 1 every time. And this does also not change if you introduce additional
protection. So there was a proposal DOMREP2 which should make this case combined secure by adding another refresh value and having a correction at the output that is masked. However, again, we have a gamma of almost 1 all the time. And this also doesn't change if we take another gadget, which was proposed, where you have the correction inside of the gadget. Can I have something to do? So it doesn't change. And the reason for all those 3 gadgets why this the security in the compositional case fails is because we are allowed to introduce some faults into the input. And here if we introduce different faults, so faults in different replications for the value A0 and B0, then the multiplication of A0 and B0 will be folded into 2 of the replications, which means that the majority vote, so the correction will always correct to the wrong value, which then leads to an output that we cannot correct. So this gives us some way to construct a gadget that is more secure, and this is another gadget that was proposed in the literature. And here you have first a refreshing and a correction of the input B, and then you do the multiplication. And in fact, this is more secure, as you can see. And if you add another correction term after the refreshing in the multiplication, you get an even better one. And actually, this is the only gadget that we analyzed that is provable, composable in the threshold combined model. And so it makes sense that it is the most secure one. Yeah, so that's it from my side. For summary, I reintroduced in this paper the random combined model and have a compositional notion for this random combined model. And what I don't talk too much about is that we have 2 tools that analyze this model and, yes, that are publicly available. Thank you.
Thank you. Questions?
Hi, in this model, how do you take care about the propagation delays between the gates and the error induced or error introduced while you are doing the calculation?
Yeah, we don't consider any propagation delays. So this model is basically on the gate level. So we just have a functional computation where we say, okay, there might be so we compute all the cases, and if there is the possibility that there is a fault because we have changed this gate, right, then we say there is a...
Because you are using more combinational circuits than the sequential circuits, so the propagation delay will be there when you are going for the practical applications. Is it any further research can we introduce some errors or assume some of the things, and then we can enhance this research?
So yes, there definitely will be a propagation delay if you look at the real implementation, right?
Yes.
And so we see this as some case to determine the probability distributions for the faults, for example, right? If you have a certain delay and you have, for example, blockage, then the propagation delay would determine the distribution of the possible faults.
And output also will be differs. Instead of what you are calculating, if I'm calculating the propagation delays, when I'm getting into that, your calculation might be also wrong in that case.
Yes, so this gives you the faults that are happening, and then afterwards, right, you don't care because then you have a blocked circuit, right, and it doesn't matter anymore.
Thank you.
Thank you. You're
welcome. First of all, thank you for a wonderful talk. Just in line with his question only, because we have sequential as well as combinational logic usually implemented in a practical implementation. So the fault, the general probability, generalized probability distribution of the faults and all those things. So what kind of probability distribution have you chosen for analysis of these things actually?
Yes. So the selection of the right probability distribution is quite difficult, especially if you want to consider a real fault injection mechanism, right? So what we did in our analysis is basically we did not have the general case, right? So we have a probability Q, which is the faults for all the gates independently. So and P is the leakage probability, which is for all the wires independently. So basically, we have a scenario where we can leak all the where faults can happen in all the gates and all the wires can leak. In the paper, we also have some other analysis where we, for example, only fault the first replication of the gadget, right? This would be something where you could implement them in all the replications in separate areas, and you, I don't know, have an EM attack, for example, where you can really only target one of the replications, for example.
So just in the same way, for say we have a sequential logic over here, so does the same thing work equally good for the sequential part, because the distribution might be different because of any other thing, or it's only limited as on date to the combinational part?
No, it's also for a sequential circuit, right? Because in the sequential circuit, you also will have, I mean, the fault will happen somewhere, right? Either in the registers, which are also gates, so you can have a model where you fault in registers, or in the combinational logic before your registers, right?
Okay.
And then you have a probability distribution for the faults happening there, and afterwards it's just the propagation of the faults, basically.
Okay, great, thank you.
Any more questions? Okay, if not, then let's thank all of the speakers of this session once more. Thank you.